Okay, next exercise 30. So here we are given a sequence an of positive integers, the first three terms of which are defined like this, and the rest of them are defined inductively like this. Each one of the rest of the terms is equal to the sum of the three previous terms. And we have to prove for this sequence that its nth term is strictly less than 2 to the power n, and this we have to do by using the second principle of finite induction. So let us see the solution. We have a1 equal to 1, this is less than 2 to the power 1 because that is 2. a2 is 2, which is less than 2 square, and a3 is 3, which is less than 2 cube. Assume an is strictly less than 2 to the power n for, okay, in fact let's just use m. We can use n also, but let's just use m because we are going to now make an assumption about all positive integers m less than or equal to n, where n is some positive integer. So am is less than 2m for all positive integers m less than or equal to n, where n is some integer satisfying this. Then an plus 1, since n is greater than or equal to 3, so n plus 1 will be greater than or equal to 4, so we can use this part of the definition to write an plus 1 as this sum, an plus an minus 1 plus an minus 2. Note that things make sense because n minus 2 is greater than or equal to 1, that is n minus 2 is also a positive integer. And now using our induction hypothesis, these things, the first one, the first term of this sum is strictly less than 2 to the power n. The second term is less than 2 to the power n minus 1, and the third term is less than 2 to the power n minus 2. Now this sum becomes equal to, if we take 2 to the power n minus 2 common out, keep in mind that n minus 2 is a positive integer, then we have 2 square plus 2 plus 1. That means 4 plus 3 is 7, which itself is less than n minus 2 times 8, which is equal to 2 cube, and this is equal to 2 to the power n plus 1. Hence, by the second principle, of finite induction an is less than 2 to the power n for all integers, all positive integers n. So that completes the solution. And there is one more exercise left in this set of exercises on mathematical induction. So let's just see that one. If the numbers a n, another similar one, if the numbers a n are defined by a1 equal to 11, a2 equal to 21, and an equal to 3 times an minus 1 minus 2 times an minus 2 for all integers n greater than or equal to 3. Also, we started the sentence with if. Then prove that an is equal to 5 times 2 to the power n plus 1 for all positive integers n. Solution. Okay, so let's just see the first two cases. a1 is 11, which is, yeah, this is true, 5 times 2 plus 1 is 11. In fact, 5 times 2 to the power 1. Like that, a2 is 21, which is 5 times 2 square, 5 times 4 is 20, plus 1 is 21. Assume this for all, or we have to make that type of assumption. For all integers, all positive integers, m less than or equal to n, where n is some positive integer satisfying. Okay, so we want n minus 2 to be meaningful. So here also n should be greater than or equal to 3. Okay. N is greater than or equal to 3. Fine. Am I taking it correctly? Because no, I think I have to take 2 here because I am going to next consider a n plus 1. So n plus 1 minus 2 is n minus 1. So n minus 1 is a positive integer if this condition is true. If we took 3 here, then also the condition would be true, but in that case we would lose the connection between this basis and the induction steps that would follow now. Okay, so this is our assumption, induction hypothesis. Then the connection is that when n is 2, then also this is true. That's what we are assuming. Then using this we would be able to say something about a3. Then a n plus 1 is equal to, now note that since n plus 1 is greater than or equal to 3, we are able to use this formula, and the formula gives us 3an minus 2an minus 1. Now because of our induction hypothesis, an has an expression like this, an minus 1 also has an expression like this. So 5 times 2 to the power n plus 1 minus 2 times 2 to the power n minus 1. Oh, there is 5, okay, plus 1. Let me continue there. Okay, so this thing becomes what? 15 times 2 to the power n plus 3 minus 5 times 2 to the power n minus 1 times 2 is 2 to the power n minus 2. Okay, so this becomes 10 times 2 to the power n plus 1, 3 minus 2, but note that 10 is 2 times 5. So if you write it as 5 times 2, that 2 can be merged with 2 to the power n to give us this. So we see that yes, the formula is also true when in place of n we have n plus 1, because here we are having n plus 1 and the form of this expression is the same as this. So by the second principle of finite induction, an is equal to 5 times 2 to the power n plus 1 for all positive integers n. These principles are called first and second principles of finite induction because there is one called principle of transfinite induction, which is there for any well-ordered set. We will see these things, okay, at some point in analysis 1 by Terence Tao, where we are going towards those things. So this completes the set of exercises that involve induction principles. Now we move to the other part, Okay, the divisibility theory of integers. Recall that there we wrongly stated one example. Let's just rectify that now. Example, this is from the second chapter. Example 2.1, which states that the expression a times a square plus 2 divided by 3 is an integer for all positive integers a. Whether this sentence itself is there in example 2.1, I don't remember exactly, but the statement is this. Now, how can one show this using the division algorithm? You see, we are not going to write sentences here, but let's just see the reasoning. The division, according to the division algorithm, A is of the form 3k or 3k plus 1 or 3k plus 2 for some integer k, and this is due to the fact that when we divide a by 3, the remainder is either 0, in which case the integer a looks like this 3k, or the remainder is 1, in which case a looks like this, or the remainder is 2, in which case a looks like this. These are the only possibilities. Now, for each of these forms, we calculate this expression. What the expression becomes, we will see that, and by doing that, we will see that in each case this turns out to be an integer. So when a is (3k), in that case a times a square plus 2 divide, in this case it's almost immediate because we have 3k outside, divided by 3. So this becomes equal to k times 9k square plus 2. So this is an integer, product of two integers. Then when a is of the form 3k plus 1, in that case a times a square plus 2 divided by 3 will be what? 1 over 3 times 3k plus 1 times 3k plus 1 whole square plus 2. Now if we expand this factor, what do we get? 1 over 3 times 3k plus 1 times 9k square plus 2 times 3k times 1, that means 6k plus 1, and that 1 and 2 give us 3. So we see that it becomes equal to 3k plus 1 times 3k square plus 2k plus 1, which is again an integer. And finally, when a is of the form 3k plus 2, then a times a square plus 2 divided by 3 becomes 3k plus 2 times 3k plus 2 whole square plus 2 divided by 3. Okay, in this case, this factor becomes 9k square plus 2 times 3k times 2. 2 times 2 is 4, 4 times 3 is 12, k plus 2 square is 4, 4 plus 2 is 6. So this is again equal to an integer, 3k plus 2 times 3k square plus 4k plus 2. So that's how we see that all integers that are one of these forms, I mean each integer is exactly one of these three forms. For any such integer, this expression a square plus 2 times a divided by 3 is always an integer. Okay, so this is the reasoning, this is the explanation for that. Now we start the exercise set, the set of exercises at the end of section 2.1. And the first one is this. Prove that if a and b are integers, with b positive, then there exist unique integers q and r satisfying a equal to qb plus r. So till this it's just like the division algorithm, but after that the inequalities are somewhat different. Where two b is less than or equal to r and this is less than 3. Naturally, to solve this exercise we are going to use the division algorithm, that is theorem 2.1. By theorem 2.1, there exist unique integers q prime and r prime such that a is equal to q prime b plus r prime, where 0 is less than or equal to r prime and r prime is less than b. So this is our ordinary division algorithm. That is, when we divide a by b, we get a unique quotient q prime and a unique remainder r prime, such that the remainder is non-negative and is strictly less than the divisor b. Then a can also be written like this. Q prime b minus 2b plus r prime plus 2b, which is equal to q prime minus 2 times b plus r prime plus 2b, where from these inequalities we can say something about this integer. Namely, 2b will be, if we add 2b throughout, then 2b will be less than or equal to r prime plus 2b, and that will be less than 3b. So taking q equal to q prime minus 2 and r equal to r prime plus 2b, we have a equal to qb plus r, where 2b is less than or equal to r and r is less than 3b. So we have proved the existence of such integers q and r. But now comes the question of their uniqueness. Let let q1 and r1 be integers that also are like q and r respectively, in this sense, integers such that a is equal to q1b plus r1, where 2b is less than or equal to r1 and r1 is less than 3b. Then a is equal to r1, so r1 minus 2b. Okay, fine. So a can also be written as q1 plus 2 times b plus r1 minus 2b. So again 2b and minus 2b cancel out, where from these inequalities we see that 0 is less than or equal to r1 minus 2b, which is less than b. So we have subtracted 2b from all the terms. Now look at this two statements, a is equal to some integer times b plus some other integer, and that other integer satisfies these inequalities. So from the uniqueness, see, unique integers q prime and r prime are unique such that this equation is true and these inequalities are true. From that uniqueness, we have to conclude that q prime plus 2 must be equal to, q1 plus 2 must be equal to q prime, and r1 minus 2b must be equal to r prime. So from the uniqueness of q prime and r prime, b must have q1 plus 2 equal to q prime and r1 minus 2b equal to r prime. But then q1 is equal to q prime minus 2 and q prime minus 2 is q, and r1 is equal to r prime plus 2b, which is r. Thus q and r are unique, and this completes the solution. Exercise 2. Show that any integer of the form six k plus 5 is also of the form 3j plus 2, where k and j are some integers, but not conversely. Every integer of this form is not necessarily of this form. Note that for any integer k, six k plus 5 can be written as 6k plus 3 plus 2, which is equal to 3 times 2k plus 1 plus 2, and that is equal to 3j plus 2, where j is 2k plus 1. So this proves that every integer of this form is also of this form. The integer 2 is of the form 3j plus 2 for the choice j equal to 0. But it's not of the form 6k plus 5, Why is it not of the form 6k plus 5? There are two ways of arguing that. One, of course, you can just simply leave the sentence, I mean, you can end the solution here itself. The justification for that is that if 2 is of the form 6k plus 5, that just means that when one divides 2 by 6, the remainder is 5. But we also know at the same time that 2 is of the form 6k plus 2, because when we divide 2 by 6, the remainder is 2, and uniqueness of the remainder proves that both of them cannot be simultaneously true. This is true because it's a concrete equation where we don't have any variable, we have only constants, and we can see that when we divide 2 by 6, the remainder is 2. So simultaneously the remainder cannot also be 5. Uniqueness of the remainder in the division algorithm prevents that from happening. That is one way of arguing for this. Another way is this: if you forcefully suppose that no, there is actually an integer k for which you have this, then since the left hand side is divisible by 2 and this term, the first term in the sum on the right hand side, is divisible by 2, 5 should also be divisible by 2, which is not true. So your supposition is wrong. So we are just simply leaving it like this because we want to be able to use the uniqueness of remainder, and without even mentioning also. Okay, you just keep in mind that this is happening because when we divide a given integer by a non-zero integer, the remainder is always unique. It's because of that whenever a given integer has one form, it will not have any other form, where of forms of the same nature. Say when you divide any integer by 6, these are the possible forms in which the integer will appear depending on what remainder it's leaving upon division of the integer by 6. So when the integer assumes one form, say 2 is assuming this form, it will not assume any of the other forms, and that is coming because of uniqueness of remainder. Okay, so then exercise 3. Use the division algorithm to establish the following. Division algorithm has been written in capital letter. So that means the result is being referred to. To establish the following. A. The square of any integer is either of the form either of the form 3k or 3k plus 1. Okay, then part B, the cube of any integer. has one of the forms. (9k) or 9k plus 1 or 9k plus 8. This means that when you divide a perfect cube by 9, the remainder is either 0 or 1 or 8. It cannot be anything else. For example, it can never be 7 or 3 or 2. And there is another part C. The fourth power of any integer is either of the form (5k) or 5k plus 1. Okay, so we have somewhat long calculations ahead of us. A square of any integer. Any integer is of the form 3m or 3m plus 1 or 3m plus 2. So we now square these expressions and see ultimately what forms they assume. 3m square is 9m square, which is 3 times 3m square okay, so it's of the form 3k, 3 times some integer. Then 3m plus 1 whole square, this becomes 9m square plus 6m plus 1, and this can be written as 3 times 3m square plus 2m plus 1, 3 times some integer plus 1, that is of the form 3k plus 1. And finally, if we take the square of 3m plus 2, we get 9m square plus 12m plus 4. 4 can be written as 3 plus 1, and from the first 3 terms, if we take 3 common out, we will have 3m square plus 4m plus 3. Because of that 3, we will have 1, and outside we will have plus 1. So again, it's of the form 3 times some integer plus 1. So when you divide a square by 3, the remainder left is either 0 or 1. Okay, so this is part A. Then part B, progressively the calculation is getting more and more, bigger and bigger. The cube of any integer is of the form 9k, okay. But we can reduce the amount of calculation, I think. Can we do something? Instead of considering all the possible because we will be calculating cube, so we can consider in fact these forms. That will be enough for the job. So instead of even writing this much, let's just look at cubes of all these three forms. So this is 27 m cube, which of course is 9 times 3 m cube. So it's of the form 9k plus 1 whole cube. So I have to expand it carefully. A cube plus 3a square b. So because of 3 I am getting 1 3, and because of squaring this I am getting 3 squares, so that gives me 27. And m square plus 3a b cube, 9m plus 3a b square, 3a b square, 9m plus b cube is 1. So if we take 9 common out from the first 3 terms, we get 3m cube plus 3m square plus m plus 1. So it's of the form 9k plus 1. Yes, that is one of the forms. And 3m plus 2 whole cube. This will be 20, just like before, 27m cube plus now 3a square b. So here, besides getting 27, we are also getting 2. So 54 m square plus 3a b square. That means b square is 4 and 3a is 9m, so 36m plus b cube, this is 8. Now from these first 3 terms we can take 9 common out. Plus 6m square plus 4m plus 8. So this last cube is of the form 9k plus 8. I hope I did the calculation correctly. Let me just verify once more, this one particularly. 27m cube plus 3 times 3 square is 27, 27 times 2 is 54. Okay. Then 3 times 2 is 6. What? No. 3 times 4 is 12. Times 3 is 36. Yes. Plus 2 cube is 8. Okay. Oh, this is not the end. We have another one. C, part C, which is even more involved. Here we have to calculate 4th power, and we have to in fact consider all the forms that we get when we divide by 5. So here the possible forms are 5k plus 1. Please write these solutions properly. Okay, like a solution would be written when you are writing an exam. (5k plus 4). So these are all the possible things. Because we are dividing by 5, there will be 5 forms corresponding to the 5 remainders. 1, 2, 3, 4, 5. Okay, now we calculate the 4th powers. Obviously there is no point actually calculating 5 to the power 4. So it's of the form 5k, where this is we have taken k. Let us take m. Then 5 it seems I have the habit of quickly writing k. Okay, now what is the expansion? The expansion of a plus b whole to the power 4 is plus 4a cubed b plus 6a square b square plus 4 ab cube plus b to the power 4. How are we figuring out the coefficients? Of course you can use the actual binomial theorem to find the coefficients, but a quicker way is to use the Pascal's triangle, since this 4 is not very big. 1 plus 1 2, you have 1 here, 1 plus 2 3, 2 plus 1 3. In fact we can start from this row also, but just to show that a part of the triangle I am doing this. 3 plus 1 4, 3 plus 3 6, 3 plus 1 4, and then 1. So 1 4 6 4 1, 1 4 6 4 1. Okay, let us now carry out the expansion. 5 to the power 4 m to the power 4. Once you have done these expansions enough number of times, you will develop an understanding of the ultimate form of the integer. You can see that in this expansion that we are going to write now, all the terms except the last one, which is going to be 1 to the power 4, they are multiples of 5. Powers of 5 appear there with positive integer exponent. So they are all divisible by 5. So ultimately this number is going to be of the form 5k plus 1. Anyway, but we have to in fact calculate the whole expansion. So this one is going to be 4 times 5 cube m cube times 1. We don't have to write that one. At least we don't have to actually calculate the values. Plus 6 times 5 square m square times 1 square plus again 4 times 5m times 1 cube plus 1 to the power 4, which is 1. So you can see that this is 5 cube m to the power 4 plus 4 times 5 square m cube plus this one 6 times 5 m square plus 4 times m plus 1. So 5 times an integer plus 1. So it's of the form 5k plus 1. Then 5m plus 2 or to the power 4. Let's just carry out this all these expansions, and then we will notice something about these calculations. 5 to the power 4 m to the power 4 plus 4 times 5 cube m cube. This time we have to write because we have 2, we don't have 1, plus 6 times 5 square m square times 2 square plus 4 times 5m times 2 cube plus 2 to the power 4. Okay. Now if we take 5 common out, 5 common out from what? From all these terms, of course. But what about 2 to the power 4? 2 to the power 4 is 16, which is 15 plus 1. From that 15 also we are going to take 5 out. So we are left with 5 cube m to the power 4 plus 4 times 5 square m cube times 2 plus 6 times 5 m square. We had m cube there, okay, fine, times 2 square plus 4m times 2 cube plus from that 15 we are taking 5 common out, so we will be left with 3 and outside there will be 1. So again this integer is also of the form 5 times some integer plus 1, that is of the form 5k plus 1. Then so we have got to 5m plus 2, next 5m plus 3, 5m plus 2, okay, so 5m plus 3, so this one will be 5 to the power 4 m to the power 4 plus 4 times 5 cube m cube times 3 plus when solving problems in number theory, it helps to use calculators. I did not bother to write the calculations here, so now I am having to write all the things. Plus 6 times 5 square m square times 3 square plus 4 times 5m times 3 cube plus 3 to the power 4. So just like before, here also this is 5 times 5 cube m to the power 4 plus 4 times 5 square m cube times 3 plus this one 6 times 5m square times 3 square plus 4m times 3 cube plus 3 to the power 4 is 81. 81 is 80 plus 1 and 80 is divisible by 5. 5 times 16 is 80. So this again it's of the form 5k plus 1. And lastly 5m plus 4 whole to the power 4 m cube 4 plus 6 times 5 square m square 4 square plus 4 times 5m 4 cube plus 4 to the power 4. Keep in mind that there is a high potential for making mistakes here, and maybe I have in fact made some mistake in not in getting the form but inside. So you carefully check all the calculations, and if there is some small mistake you rectify it, and if you want you can let me know also. Okay, so here again 5 cube m to the power 4 plus 4 times 5 square m cube times 4 plus 6 times 5 m square 4 square plus 4 times 5 times 4 cube plus, now what is 4 to the power 4? That is 4 square whole square, that means 16. I think it's 256. Yes. And if one divides 256 by 5, then of course one can in fact write 256 as 255 plus 1. Now if one divides this by 5, then one gets this. So that means we can take 5 common out from this term. Plus 1, again it's of the form 5k plus 1. Okay, now we come to that thing we were mentioning about, we were saying that we can notice something in these calculations. Note that ultimately whatever form the powers assume is determined not by the 5m part of the forms but by the remainders. You see, when the remainder is 0, here also the remainder is 0. 0 to the power 4 is 0. When the remainder is 1 to the power 4, because you see, when we expanded these expressions, the last term is what determined all the things. From the last term, sometimes we have been able to take multiples of 5 inside this 5 times. Whatever is left ultimately determine the form of the power. So 1 to the power 4 is 1, 2 to the power 4 is 5 times 3 plus 1. So this part was engulfed inside that 5m. 3 to the power 4 is 81, 5 times 16 plus 1. So this part did not matter in finding out the form of the final number, final power. And finally 4 to the power 4 is also this thing, this observation will lead to modular arithmetic, or the arithmetic of remainders, where you have this type of relations. 4 to the power 4 is congruent to 1 modulo 5, where only the remainder is what matters. Multiples of the number by which we are dividing, that does not matter, that amounts to 0. We will see these things in the next chapter, I think, or next section. I can't remember clearly, but we will see these things. Okay, so this one was a slightly long one. Then exercise 4. Prove that (3a square minus 1) is never a perfect square. And in fact hint is also given. Because of this hint, practically we don't have to do anything. Exercise 3a, that means the part A of the exercise we have solved just now. Note that (3a square minus 1) is of the form 3 times. In place of minus 1 we can write minus 3 plus 2. So the entire integer can be written like this. In other words, 3a square minus 1 is of the form 3k plus 2, and according to the previous exercise, the square of any integer is either of the form 3k or 3k plus 1. So since this is not any one of those forms, so such an integer can never be a perfect square. So by exercise 3a, we can just directly write 3a square minus 1 is never a perfect square. Whenever we are in number theory, at least in that part of number theory which concerns only divisibility and nothing specifically is mentioned about a variable. For example, here we are not saying what a is. Then you have to assume that such a variable is an integer. Then exercise 5. For n greater than or equal to 1, that is for a positive integer. Here also you see we are not saying anything. Had it been analysis, we could not have, although we usually use n to denote integer, but one can argue that since nothing is said, I can also assume n to be a real number. When n is a real number, then also this inequality makes sense, but in this context n is an integer. So for a positive integer n, prove that n times n plus 1 times 2n plus 1 divided by 6 is an integer. If you recall, this is actually the sum of the squares of the first n terms. We have already seen this in the previous set of exercises on induction. But of course, that's not how we are supposed to solve this. We are supposed to use the division algorithm and remainders to solve this. In fact, a hint is given. By the division, elaborate hint is given. By the division algorithm, n has one of the forms. One of these forms, 6k or 6k plus 1 or 6k plus 2, like that. We are not writing everything up to 6k plus 5. Establish the result in each of these 6 cases. So you know what you have to do here. You just pick one of the forms one by one, put them here in place of n, and verify that the expression is an integer. So that's how you have to just solve this exercise, and I'm not going to do it. Okay, I leave it to you. For example, for the choice 6k, you can immediately see that 6 cancels with 6 there in the denominator, and you have an integer. For the other choices also, you will see that this becomes an integer, this expression. And if one is simply given this exercise, not like it's given in this set of exercises, but as simply an exercise alone, then one can also argue like this: since we know that the sum of the squares of the first n natural numbers is equal to this, and that sum is an integer, so this is also an integer. So do it yourself. Okay, then exercise 6. Show that the cube of any integer is of the form (7k) or 7k plus 1 or 7k minus 1, which has been written together like this: 7k plus minus 1. We know what to do, so let's just do the calculation. All integers are, each integer is one of these 7 forms. (7k plus 3, 7k plus 4, 7k plus 5, 7k plus 6, and let's now calculate cubes of each one. This one of course is 7 square k cube, so it's of the form. Okay, let me just write the equations like this. That way they will be easier to make out, easier to see. From the experience gained from that calculations, those calculations, we can almost see here that this will be of the form 7 times something plus 1, because all the terms involving powers of 7 that are positive integral powers, they will contribute 7 times something to that term. The only non-trivial term, or the only term that matters here, is 1 cube. So can we simply write 7 times m plus 1? Oh, we have okay, it does not matter, but still let's just use some other variable name. 7m plus 1, 7m plus 2, 7 plus 3 Actually, I will leave this part to you. You are supposed to expand this and then make sure that ultimately you have an expression like this where k is a suitable expression, a suitable integer that involves powers of m along with powers of 7. 7mc, again I am writing k. Multiples of 7 will occur in this expansion along with 8. That 8 can be written as itself as 7 plus 1. So ultimately this again is going to be of the form 7k plus 1. Okay. This one will have again multiples of 7 plus 3 cube, which is 27. 27 can be written as 28 minus 1. So this is a multiple of 7. This along with the other multiples of 7 give us one multiple of 7 minus 1. Okay. So do you see how the actual expansion in the end does not matter, although we do have steps in between, expressions in between. Seven m plus 4 whole cube. So here we will have 64. Is 63 plus 1. So which 63 is again a multiple of 7. So in this case the power is of the form 7k plus 1. Then 7m plus 5. Here we have 125. Okay, what is happening? I think 128. No, 128 won't give me that thing. So what I am trying to see here is 124 or 128. This is my problem. If it becomes really large, then my brain hangs. Numerical calculations. Okay, let me think of this one. Let me just simply divide. Okay. 126. So that means 125 is 126 minus 1, and 126 is 7 times 18 minus 1. So this one will be of the form 7k minus 1. And then finally 7m plus 6 whole cube. Here one can in fact apply a slightly different trick to minimize the calculation. Instead of working with this, one can also observe that 6 can be written as 7 minus 1. So here we have 7 times m plus 1 minus 1 whole cube. Now if one expands this, except the last term, the other terms will all have 7. So they are all multiples of 7. And the last term is minus 1 whole cube, which is minus 1. So that means this will be of the form 7k minus 1. So we did not have to deal with 6 cube and then figuring out whether minus 1 or plus 1 comes. So we have shown that cubes of all possible integers are of the form either 7k or 7k plus 1 or 7k minus 1. Exercise 7. Obtain the following version of the division algorithm. This is like the first exercise. Okay, so what is the version? For integers a and b, with b not equal to 0, there exists unique integers q and r that satisfy a equal to qb plus r. So all these different versions of division algorithm are the same in this equation. The only difference is that the inequalities that the supposed remainder is to follow, so those inequalities differ, where minus 1 over 2 times the absolute value of b is strictly less than. Okay, so this time here we have strict inequality, that is less than r, and r is less than or equal to 1/2 of absolute value of b, and hint is given. In fact, the hint is here so elaborate that itself is a solution. First write a equal to q prime b plus r prime, where r prime is non-negative and strictly less than the absolute value of b. So this is coming from ordinary division algorithm. When now cases will arise depending on what r prime is. When r prime is non-negative, of course it is non-negative, and less than or equal to 1 by 2 times mod b, then let r equal to r prime and q equal to q prime. Okay, and then if these inequalities are true, then automatically these are also true, because this is a negative real number which will be strictly less than 0. So automatically it will be strictly less than r prime. So this is one case. And when the value of r prime is, it exceeds this, let r equal to r prime minus absolute value of b and q equal to q prime plus 1 if b is positive, or q equal to q prime minus 1 if b is negative. Since b is a non-zero integer, it is either positive or negative. Depending on what it is, we have to make these choices. If you follow this hint exactly how it is given, that is the solution. You just have to make sure that in this case, in the first case where these inequalities are true, we can clearly see we get what we want. In the second case, you just have to make sure that yes, here also you are getting the required things. Okay, then so this one, for this one I would just write follow the given hint. Then exercise 8. Prove that no integer in the following sequence is a perfect square. hint a typical term. This type of numbers have a name. They are called repunit numbers or repunits. It means repeated unit because the only digit in these numbers is 1, so that is the unit element in the ring of integers. So that's why this type of numbers are called repunits. Prime numbers that appear in this list are of interest. For example, 11 is a prime number. 111 is not a prime number, it's divisible by 3. So far, only a finite number, I think 5 or 4, I can't remember exactly, repunits have been known to be primes. It's still not known whether there are infinitely many repunits that are primes or only finitely many of them. So that is still an unsolved problem. Anyway, so this type of numbers can never be a perfect square, and the hint is this. A typical term can be written as (108 plus). It's not 108. I mean the last 3 digits are 10 and 8. And since, I mean, from the form of this integer, you can see that this integer is divisible by 4. So the actual repunit is of the form 4k plus 3. And from a previous discussion when we had the division algorithm, and after that we were discussing its applications, there we saw one thing, that the square of any integer is either of the form 4k or 4k plus 1. It becomes it is of the form 4k when the integer is even, and when the integer is odd, its square becomes 4k plus 1 for some integer k. So it never becomes 4k plus 3. So that's why no integer of this form is a perfect square. Here also you can see that you can just simply write the whatever is given in the hint properly, and that will be a solution. So this also I leave to you. Follow the given hint. Exercise 9. Verify that if an integer is simultaneously a square and a cube, simultaneously a square and a cube. An example is also given, as is the case with 64, which is 8 square, but at the same time it's also 4 cube. Then it must be either of the form 7k or 7k plus 1. Okay. To write this solution, we can take the help of exercise 6, because there we have seen that the cube of any integer is either of the form 7k or 7k plus 1 or 7k minus 1. Okay, so by exercise 6, the cube of any integer has one of the forms 7k, 7k plus 1 or 7k minus 1. We are now going to see what happens to the square of an integer in terms of this type of forms when we divide an integer by 7. So for that I am not again going to write things, we will just look at all the possibilities. Seven m plus 4, 7m plus 5, 7m plus 6. So for all these forms we are going to calculate squares. 7m square is of the form 7k, 7m plus 1, and in carrying out these calculations again we are suppressing actual amount of calculation and writing the final form. But at the same time being careful that whatever we are writing, it makes sense. I urge you to actually calculate these powers. Okay, you expand them and then make sure that the ultimate form is really this. 7m plus 2 square. So here we will have 2 square is 4. Okay. Okay, so this is of the form 7k plus 4. Three square is 9. From that 1 7 goes inside, so it's of the form 7k plus 2. 4 square is 16. 16 is 14 plus 2. 14 goes inside, so it's of the form 7k plus 2. 5 square is 25. So 25 is 21 plus 4. That 21 goes inside and gives us a multiple of 7, and we have 7k plus 4. And finally 7m plus 6. 6 square is 36. So that is 35 plus 1, and 35 is 5 times 7, so 7k plus 1. So among these forms, you can see that 7k minus 1 does not appear anywhere among the squares. The squares are of the form, okay, by the way, what is 7k minus 1? 7k minus 1 is actually 7k plus 6 minus 7. So this is 7 times k minus 1 plus 6. So this form is the same as 7 times something plus 6. That we don't see anywhere here among the squares. 7k plus 1, 7k plus 4, 7k plus 2, again 7k plus 2, 7k plus 4, 7k plus 1. 7k plus 6 does not appear here. So that means 7k minus 1 does not appear. That form does not appear among the squares. So that just tells us that the possible forms are either 7k or 7k plus 1 if the integer is simultaneously a cube as well as a square. Okay. So you can just write, since the form 7k, I'm just crudely writing it, okay. When you write the full solution properly, you just include this part. Since the form 7k minus 1 does not appear among the squares of any integer, the possible forms are 7k and 7k plus 1 for an integer that is a cube and also simultaneously a square. Then exercise 10. For any positive integer, establish that the integer n times 7n square plus 5 is of the form (6k). So in proving these many results about the form of a given integer, you can see that this one tells us something definite. It says that any such integer is always divisible by 6. Now, instead of looking at all the possible cases that arise, all the possible forms that arise when one considers division by 6, we can reduce the work here by writing a solution like this. Note that n times 7n square plus 5 is equal to n times 6n square plus 6 plus so we have one more n square and one less n. I mean what I meant to say is that we have one less n cube here that we have added and one more n here that we have subtracted. Okay. Since no, okay, we can't start like this. If n is even, then n times n square minus 1 is also even, because n is divisible by 2. If that is the case, then this is also divisible by 2. If n is odd, then n plus 1 is even, and so n times n square minus 1, which is n times n plus 1 times n minus 1, is also even. So we see that in any case this part of the sum is always an even integer. Thus n times n square minus 1 is always even. Now if we can show that this is always also divisible by 3, then it will be a multiple of 6. Now, okay. Can we really conclude like that? Here we have shown that this is of the form 2k always. Then simultaneously, if we also show that this is of the form 3k, from that can we say that it's of the form 6k? We can say, but for that we would need a fact about prime numbers which we don't have yet. Okay, I did not notice this before. So instead, okay, this was a nice attempt at reducing the calculation labor, but I don't think we have the tools to properly conclude that this is also a multiple of 6 this way. Instead, you can just follow the usual boring route of considering all the possible forms. Put each one of them in place of n here, because here we can clearly see it's of the form 6k. We just only want to make sure that this one is also of the form 6k, so that the total number will be of the form 6k. So you put each form here and verify for me that that is the case. At least here the calculation is not going to be that big if you argue like this. So this is left to you, it's incomplete. Then exercise 11. If n is an odd integer, show that n to the power 4 plus 4n square plus 11 is of the form 16k. Okay, since n is odd, we have n equal to 2m plus 1 for some integer m. Thus, so we just now have to do the calculation and conclude that yes, it's of that form. It's divisible by 16. 2m plus 1. Keep in mind that these shortened calculations are only for saving time and at the same time understanding what is really going on inside the calculations. When you write a solution, if you cannot logically justify writing these things, that is, if you don't say why you are going to ultimately get a form like this, then that will be an incomplete solution. So what I am trying to say is that when you write the solutions, you actually have to do all the calculations. Okay, until we get to the arithmetic of remainders or modular arithmetic, we won't have this facility of neglecting multiples of 7 or things like that. We can, of course, it will be justified, but for that justification we need something, we need some sort of result that we don't have now. So here, for example, for one last time, I am again going to write all the expansions. Two to the power 4 m to the power 4 plus 4 times 2 cube m cube plus, oh, this is going to be big, 6 times 2 square m square plus 4 times 2m plus 1 plus 4 times 4m square plus 4m plus 1 plus 11. Okay, now we try to take 16 outside. Okay, can we do that? From these terms, of course we can take 16 outside because we just need 2 to the power 4 that we have here. Here also we have, due to the presence of this 4. Here also, oh, do we have it here? What happened? 6 times 2 square times m cube. Oh, but we are going to have other m cubes also, so we can't take 2 to the power 4 outside yet. We have to write one more step, plus 16 times, so for 16 we need 2, so 1 2 is left, plus m cube, we are going to get another m cube here. do we get another m cube? No, we don't get another m cube actually. We get m square, fine. So we can keep it like this. This, however, we have to calculate. 4 times 6 is 24 m square plus 8m plus 1 plus 16m square plus 16m plus 4. Okay, plus 11. So 16m to the power 4 plus 16 times 2m cube plus 24 plus 16. M square plus 24m plus 4 plus 1 is 5, 5 plus 11 is 16. So this is 16 times m to the power 4 plus 2m cube plus what is this? Oh, what? I think I made a mistake, or 24 m square m square. Definitely I have made a mistake somewhere. Four times 2m plus 1 plus 4 times 4m square plus 4m plus 1. Okay, so we are having difficulty not with these terms but here. Or I took the question down wrongly. That may also be a possibility, just like that time where we wrongly wrote this. Not we, it's me. Because I don't see any mistake here. Do you see anything? Of course you won't be able to say it now. A to the power 4 plus 4a cube, okay, plus 6a square b plus 4ab cube plus b to the power 4 plus 4 times 2m plus 1 whole square, so 4m square plus 2 times 2m is 4m plus 1 plus 11. Okay, so this one is 16m to the power 4 plus 16 times 2m cube plus 24m square plus 8m plus 1 plus 16m square plus 16m plus 4 plus 11. So 16m to the power 4 plus this thing, yes, this is 40m to m square plus 24m plus 16. Oh, I think there will be another step or what? These three, okay, I think it's not going to come this directly. These three terms of course have 16 in them, but what about these two terms? They seem to be missing a 2. That is the problem, no? Here 5 times 8. If I have another 2, then I can take 16 out. So what is the, oh yes, yeah, now I get it. So from these three terms we have 16, and now this can be written as, we can take the 8 outside. Okay, now if we take 8 outside, then 5m square plus 3m. Now what I thought is still not coming, or is it coming somewhat more indirectly? Let me write one more step. Plus 8 times 5m square. Instead of writing 3m, we can also write 5m minus 2m. Okay. Now plus 8 times 5 times m square plus m minus 2m. This is already giving us 16 m actually. So that we can merge with this one, writing minus 16m, so minus m plus 1. Now you see this, plus 8 times 5 times m times m plus 1. Okay, now you see, either m, since m is an integer, either m is even or it's odd. When m is even, then of course we have a 2, the desired 2 that we need to make it 16. If m is odd, then m plus 1 is even, so there we will have a 2. So I leave it to you to complete the exercise. You just have to write that m times m plus 1 is always even, because when m is even, then it's even. When m is odd, m plus 1 is even. So this is always even, so it's going to give us a 2, and that along with 8 will give us 16. So ultimately the whole thing is a multiple of 16. So it's of the form 16k. So with this set of exercises is over. So in the next video we will see a new section. We will see new things. And tonight I am going to upload our usual we have ring theory today, no? So ring theory problems will be uploaded, their solutions. And tomorrow, along with a Gaussian video, Gaussian exercises, I will upload one graph theory video. And then after that, the things will go on usually, following the usual schedule. So with that, I end this video. This is me, Lucifer, from A Mathematical Room. Have a nice day.